My name is also Hutchinson, and I'm currently on spring break right now, so I really don't want to be doing this, but here's my lab 4 report about circuits. Just a little introduction. The purpose of this lab is to use principles of energy conservation and current conservation to predict behavior of circuits, and in case there's a series in parallel, then use a multimeter to measure the actual values of the current and potential differences in the circuits. Preview result. Experimentally measured RC value matched up with the actual value in 6 seconds. System of the circuit surrounded everything else. The assumption we made was the resistance of wires is negligible. Some of the fundamental physical principles used in this lab are Ohm's law, delta V equals IR. Everyone knows that conservation of energy and charge. The total energy and charge in the system remains constant. Kirchhoff's node and loop rule, which say that total current flowing into a node is equal to the total current flowing out of the node. And then loop rule says the delta V for closed loop equals 0. Now I'm just going to go through each step of the experiment. First, I simulated this circuit down in the bottom left in the online circuit simulator provided for us in this lab. And then I used Ohm's law to find the current flowing through the circuit. And as you can see on the right, negative, so that line is correct. If you see the direction of how the energy is hooked up in the circuit, there's no change in the current reading, so it is okay. And down in the bottom right, you can see I use a voltmeter to measure the potential difference across each part of the circuit between all the components. Here's a graph of the electric potential versus the position of circuit of the circuit from the last slide. As you can see here, A to B goes up as it's crossing through the batteries, and then stays constant while it's just like the wire with no components, and then over the resistors it goes down, obviously, and at the end of the circuit it returns to 0 as expected. Now just a note, with the voltmeter attached, the current in the circuit doesn't change because the voltmeter has a really high resistance, so current is not going to flow through it. But in this step I attached an ammeter in parallel with one of these resistors here, and the total resistance of the circuit increases. That's a typo. It increases, and then current through the whole circuit increases because the current flows through this new path through the ammeter, because it has no resistance, and it's going to take the path of least resistance. And then here I just went through and calculated all the resistances for each component of the circuit using the potential differences that I found using the voltmeter earlier. You can see that for each one. 47, 100, 0, 0. Now for this next part of the lab, I built this RC circuit in the simulator that you see on the right, with a 200 millifarad capacitor, and used different bulbs for each step. But here I found that the time to charge up the capacitor using a 10 ohm bulb was 15 seconds, and then to discharge that capacitor was 20 seconds. Then I found that the time to charge the capacitor with a 20 ohm bulb was 30 seconds, and the time to discharge it was 40 seconds. Now for this next step, I used essentially the same RC circuit in the last step, except with a 30 ohm bulb. I pretty much gathered all this data in the simulator, using the stopwatch in the simulator to create this graph of ln of current voltage over V0, which was 9 volts, versus time, and then use the slope of this graph to find the experimental RC value, which was 6 seconds, as you can see here. And then I ran it in the simulator regularly, and found that the actual RC value was also 6 seconds, which are obviously the same thing, which is pretty cool, I guess. And for the discussion questions, what if this lab was done in real life using an actual ammeter rather than an idealized ammeter? It would not actually have no resistance, so some of the current would end up flowing through the path of the resistor when the ammeter was connected in parallel with it. However, in the simulated experiment, all the current went through the parallel ammeter because it had 0 resistance, which is obviously not realistic. And then what if this lab was done in real life and an actual battery was used to charge a capacitor with no resistor in the circuit? Using what we saw in the simulation, we would probably predict that capacitor would charge nearly instantaneously, but in real life that would not happen. Um, because real batteries, that's also a technical type I guess should be said collaborative, but real batteries have some internal resistance, so the capacitor would not actually charge instantaneously. Yeah, that's pretty much it. Thank you for watching.